Hi there, welcome to another day of physical science. This is your Phys Sci Coach Powers, and today we're going to be talking about Newton's third law. So let's get right on into it. Our objectives today are to describe Newton's third law, the pairs of forces, action and reaction forces, to identify the substances that have momentum. Let's think about what momentum is and what kind of things have momentum, and to calculate momentum using a formula. So, action reaction. This is Newton's third law kind of summed up. You can think of any action force and then there's a reaction force. What does that mean? Well, we're going to go through a couple different examples here, but it's important for you to remember that when one object exerts a force on a second object, the second object exerts a force on the other object, that first object, in equal and opposite direction. Okay, equal in size, opposite in direction. So if they are balanced, then you have no motion, just like we've been talking about, right? But there is still an action and a reaction force that is taking place, okay? So remember that these forces are not canceling each other out, all right? They're not necessarily balanced forces because the forces are acting on different objects. So if you think about a rocket, for instance, and you can think about or how about a balloon? Let's just start something a little bit easier. If you're blowing up a balloon and you let that balloon start to get itself deflated, right? Well, what is the action force in that case, right? So the action force is the air is going to be, whoa, a little funky looking there, leaving the balloon, right? And so if we can kind of imagine a picture of that, we've got the little balloon valve there, and we've got the air going in one direction, right? But the balloon actually doesn't move in that direction, does it? The reaction is going to be that the air is actually pushing on the balloon, okay? So you can think of the action as the air is exiting the balloon, but if we think of the reaction, what's happening is that air is actually pushing back on the balloon in that direction. Okay, so the balloon is actually moving forward because the air is pushing it forward. The air is acting on the balloon. Okay, the balloon is acting on the air basically as it leaves, but the air is acting on the balloon. And so remember that these forces are acting on different objects. One is acting on the air, the other is acting on the balloon. And because they're not equal, then the balloon is going to be moving forward. All right, it's going to be moving in this direction because those forces are not equal to each other. All right, so they don't cancel, they're not balanced. In this case, they are acting on the different objects, and so we actually have motion in this case. Here's another example of two different forces that are not equal to each other. If you imagine a soccer ball coming down from Earth, you can imagine that the Earth is pulling on the soccer ball more than the soccer ball is pulling on the Earth. All right, so there are two forces at play with the force of gravity, the acceleration due to gravity, right? So the action force of the Earth pulling on an object and causing it to fall is much more obvious than the equal and opposite reaction force of the falling object pulling on the Earth. All right, so those are both equal to each other, but because that Earth is way more massive, you are not going to see that Earth moving in an upward direction, okay? The soccer ball is moving in the downward direction, right? All right, so another good example is when you think about swimming. So if we look at the swimmer here, we can see that when that arm is moving back, all right, as you are trying to push yourself forward, the action force is the swimmer pushing the water backward, but the reaction force is the water that pushes the swimmer forward. So just like that balloon, this is a good example. You have an action and reaction. Now, this swimmer is presumably going forward, right? And that is because the reaction force is going to be greater than the action force in this case, all right? And so that's why the swimmer is going to go in a forward direction, okay? All right, so another good example to think about, if you guys have seen the movie Passengers, and the character played by Jennifer Lawrence gets stuck in that big bubble when the gravity goes off in the spaceship. What's happening there? Well, you can also look at the bottom here. This guy is wringing out a washcloth or a paper towel, and he is actually in 0G. And you'll notice that the water isn't falling down to the ground because he's in 0G. So what happens to the water? It basically stays in this bubble because the cohesive forces of the water are strong enough that it holds itself in place. And so the water doesn't actually leave the washcloth completely because it's still a cohesive layer around the entire washcloth. Well, does that mean in this example with Jennifer Lawrence being stuck in this huge swimming pool bubble, does that mean that she will not be able to move her way, through the bubble? Well, again, think about action and reaction. Is that water going to have emotion? Is that water more massive than she is, right? So, we can think about the earth and how massive it is, and yet we can't see the action of the soccer ball pulling on the earth. Well, would her movement as she tries to swim, would that move her forward? I think it would. I think we would see her swimming forward, and in the movie, she kind of just seems to be stuck. She can't go anywhere. I think you would be able to swim out of a motion like this. Now, would you be able to swim as quickly? Perhaps not, right? Because now you have to move the entire bubble, which is a great deal of mass. You have to move that entire bubble through the space instead of just moving you through that space of the bubble. So you could be talking about the fact, well, yeah, it might be kind of seeming like you're staying in place because your reaction force might not be as, having as great of an effect as it would in a regular pool. I don't know. Fun thing to think about, right? Let's think about rockets and how rockets work. You can see that here in this screen, we've got hydrogen and oxygen are going to be mixed together in a combustion chamber. That's what's going to cause the explosive force, right? Hydrogen burning, basically. And as that happens, then the gas is going to push the rocket forward because the rocket is pushing the gas backward, right? So the rocket is pushing out the gas and the gas is pushing on the rocket, and this is what makes it work. And it's really important that you realize this because a lot of times we think of a rocket being able to blast off of the surface of the earth, and we think about the rocket's force pushing against the earth like we would be jumping, okay? Like we would jump up into the air. The rocket is pushing on the ground like we push on the ground with our feet. But that's not the case. It's really important to realize that the rocket has its own propulsion system inside of it, that it is the actual gas leaving and then the gas pushing on the rocket that makes the rocket actually go up. But it's not because it pushes against the earth, all right? Because remember, in space, a rocket can still move. And if you're in space and you push against space, you're not going to go anywhere, right? If your legs are there and you try to pretend to jump in space, you're not going anywhere. And that's not the case for the rocket. The rocket has its own propulsion system, and so it can push against itself in a sense, right? Those gases push against the rocket and propel it forward. Your legs can't do that. So this is very different. And again, the reason that the Jennifer Lawrence situation could still work out in passengers is because she is pushing against some mass, right? She has some mass that she is working against, and so she is able to move forward, or at least in the opposite direction as the bubble. And how fast, I don't know exactly, but she would be able to move forward. And that's not the same as you pushing against space where there's nothing. If you have matter to push against, you're going to be able to have an action force and a reaction force. All right, so let's talk about momentum. Now, momentum is summarized with the formula that you see there. It's defined as the product of the mass and the velocity of an object. So it's P equals mv. And M stands for the mass, right? So our mass is going to be measured in kilograms or grams. Oh my goodness, come on now. Mass is measured in, well, hello. Why are you being difficult? Mass is measured in kilograms or grams. And then velocity we've talked about before, measured in meters per second, but it includes a what? It includes a direction. Don't forget that whenever we're talking about velocity, we are talking about something that has to have a direction, okay? Which means since momentum has velocity, that means momentum must include what? Yeah, it must include a direction. So anytime you're writing out the momentum of a substance, make sure that you're writing out a direction as well. And so what's the unit for momentum? Well, it's kind of interesting, but it's just a kilogram meter per second, okay? So it's kind of a long unit, you might think. Kilogram meter per second, not too hard to say. What does it mean? Remember, it's the product of the mass and velocity of an object. What does that really mean? It means that every object that has mass and has some velocity is going to have momentum. Okay, now we've learned about a lot of different things. We've learned about inertia, momentum, acceleration, velocity. A lot of these things kind of get jumbled in your head. So make sure that you start distinguishing what these different terms mean and how they actually act on forces. All right, there's a lot of practice questions that you can practice on page 415. But I want you to think about momentum in terms of force. Okay, because we've talked about force as well. We learned that force is mass times acceleration, so it has to do with mass and acceleration. But this is a mass and velocity situation. So it's a little bit different. But what that basically means is that momentum can change over the distance that a momentum is applied. So imagine a kid that is going to be absorbing a baseball in his glove. Now, if he goes out toward it, that's going to feel a little bit different than if he absorbs it and pulls his arm back a little bit, right? So as the period of time of that change in momentum, my velocity is changing, right? My mass of my baseball doesn't change, but my velocity is changing. So if I can change, how much time it takes for that velocity to change, instead of just going, I go, woo, then I'm going to be able to see that the force needed to cause that change becomes smaller, okay? In other words, if I can pull my hand back, it's not going to have as much force as if I am pushing forward into it, right? Or if I hit it straight on. So the time over which you are changing momentum will change the amount of force necessary in order to induce that change. Okay, so momentum and acceleration are not the same thing, right? Momentum and force are not the same thing. Distinguish those things in your mind. Force is related to acceleration, and that is based upon, if I have increased acceleration, I have increased force. But if I'm talking about the force and momentum, a lot of times I just want to talk about how much time does it take to, see that change take place. Anyway, I'm kind of belaboring that point. Let's go for it. All right, so let's see what we would do if we wanted to solve a problem of momentum. What do we do with a problem like momentum? You're going to calculate the momentum of 6.00 kilogram bowling ball moving at 10.0 meters per second down the alley toward the pins. All right, so let's see how we do this work. We want to show our gems. All right, so first we list our givens. So this is the G of our gems, right? And so we do mass and velocity, and then we have to write down our unknown and put its units. And now we have to do our equation, right? So our equation is mass times velocity. And remember, this is kind of an unusual symbol. P stands for momentum. You're like, what? Where'd that come from? It's okay. I know it's weird. But yeah, P is momentum. It actually, I think, is the Greek origination, but don't worry about it. It's just the way you got to memorize it. P equals mv, all right? And so now we have to see, do we have to rearrange my equation? No, we don't have to rearrange the equation. Remember that our equation is going to already be set up because P equals mv is what we're looking for. All right, so, I don't want a laser pointer. Oh my goodness. All right, so then we get our known values, and so we substitute and we put our 600 kilograms and our 10 meters per second in that spot, and so we get our answer of 60 kilograms per meter, 60 kilogram meters per second. And now we have to include that direction toward the pins. You're like, well, how do I know what the direction was? Well, you got to go back to the original question, because that original question talked about the, oh, come on. Why has it got to be difficult? Toward the pins, right? And so that original question talked about the direction, so you have to make sure you include that direction in your solving of momentum. So that's how you do a momentum problem. Again, you can practice a few more of those on page 415, I think it was. All right, now to finalize or finish up this lecture, we want to talk about the law of conservation of momentum. And this has to do with the idea that as objects are colliding, that the overall momentum of the objects before and after collision are the same. The momentum can be transferred from one object to another, but it just doesn't disappear, okay? So if I have the total amount of momentum in an isolated system before and after a collision, I'll be able to see that they are the same, okay? So you can kind of imagine like a couple pool balls, and if I have, wow, that's a nice looking pool ball. Let's just go ahead and color that one in a little bit since it's not exactly a circle anymore. If I have one pool ball and maybe that one is 1 kilogram, okay, and then let's say I have I don't know, like a ping pong ball or something, okay, then if this thing shoots out at the ping pong ball, which let's say is just like, I don't know, 25 grams or something, I don't know how how big a ping pong ball is, then that momentum, the m times the v, right? So the mass times the velocity. And so if I were like, oh, this is 1 meter per second, and it's a 1 kilogram mass, then what is the overall momentum going to be as it leaves? Well, if this ball, if the big billiard ball completely stops, and all the momentum is going to shift into this ping pong ball, it's going to shoot out of there like a rocket, right? It's going to go really fast. However, if some of the momentum is maintained inside this billiard ball, then this ping pong ball won't go out as fast. The billiard ball will keep moving. And in fact, what would we expect to happen? Yeah, we'd expect this billiard ball to just kind of run into the ping pong ball and keep moving through, and the ping pong ball would move off faster. But you're not going to convert all of your momentum from one object to the next object. So you're going to have to just add these things up. So the overall momentum as you leave, let's say, if this one left and as that one left, why did I all of a sudden lose my pen? Why is that happening? If this one left and, let's say it left at 5 meters per second for whatever reason, then I would be multiplying, we'll convert that one to kilograms, right? And then I would be multiplying these things, and I would say, okay, well, how much is this one? 5 times 0.025, and I would be, well, let's just go ahead and do it real quick, just because math is fun, and we want to. So if I said 5 times 0.025, then, then I've got, okay, let's try that again. 5 times 0.025, my 2 doesn't work. I know I should do this in my head, right? So my momentum would be oh, you did it again, you little turkey. Why is it doing it? I don't know. All right, so we would have 0.0125 as our overall momentum, okay? Kilogram meter per second. And then over here, I had 1 times 1, and so we were at 1 kilogram, okay, meter per second, which means that if you just subtract those two, right, you're going to end up having 0.875. That means the momentum after they collide. You're still going to have a lot of momentum in this object here, right? You're still going to have 0.875 kilogram meters per second of momentum in that original billiard ball as it's moving. So it's still going to be moving, and you could then figure out how fast it's moving, right? And this is kind of the cool part about the math. So if I now have a total momentum of 0.875, when we solve this problem for velocity, right? So if P equals mv, and after I leave, I have 0.875 kilogram meters per second. My mass of my billiard ball hasn't changed, right? So I still have a 1 kilogram billiard ball, but now I have a new velocity. So now to solve for my new velocity, oh really? Why do you just disappear like that? I don't understand what's happening. I just have to divide both sides by 1 kilogram to get my velocity by itself, right? And so now I know 0.875. Oh, well, that means that my speed has now changed to 0.875 0.875 meters per second, because my kilograms would have canceled out, right? And so now I have slowed down my billiard ball, but I haven't slowed it down much. I've slowed it down to 1 meter, from 1 meter per second to 0.875 meters per second. I shot my little ping pong ball off at 5 meters per second. It did slow my billiard ball down a little bit, but not that much comparatively. So anyway, kind of fun to be able to take the math and follow it through to see what's happening there. Let's see what we learned. And we learned what happens when an object exerts a force on another object. Okay, for every action, there's going to be a reaction, right? So we're going to see some sort of movement typically, unless they happen to be exactly the same forces and they're acting, in this case, remember, they act on different objects. How do you calculate the momentum of an object? P equals mv. What's the total momentum after objects collide? It's conserved. It's got to be the same as it was before they collided. So there you go. That's what we learned today, and I hope you have an awesome day, and God bless you. Be kind to one another. See ya.